Mhm. All right. Shall we start?
Yes.
So, hello together. So today we're gonna basically cover the rest of the lecture. And so far, what Dan and Max basically taught you or went over with our strict forward, feed forward networks like are good at stuff like predicting images, like labeling images. Okay, we see image of a dog, and this network is able of classifying as a dog. We've at some point also introduced stuff like fully convolutional networks, where at some point able to do semantic segmentation. So we can label basically every single pixel in an image. And it doesn't really matter what size the image is, we can just run it through our model and it will give us a prediction. But what happens if we have something like semantic segmentation of a video frame? Like we have multiple images that are coming in and we want to segment or just classify objects in multiple frames. What general assumption are we breaking here that we have in machine learning that is really important with these images? Can you guys answer it? Like if we have multiple image frames that we want to classify in a video frame. The chat, I80, perfect. So obviously these images are not independent anymore. Like the I don't know the probability that there's a car in this frame obviously depends on the probability of there being a car in the previous frame. So suddenly our normal work and networks that we're using so far don't really work anymore. Or what happens if we want to produce a label for an image, right? Three people on a kite. Suddenly we have multiple outputs to a single image. I mean, we could try to create some kind of a network with multiple outputs, but what happens if we want to create seven outputs suddenly or three outputs? I mean, this will break down pretty quickly. And also the next problem is people obviously also depends on the output before it, like on three, and depends on people and so on. So we somehow have to create this um this new version. And to think about it for a while, you might come up with this idea of using something like an RNN. So unlike our previous models, we sort of, in a way, have two inputs to our model. We have the state from the previous time, which is usually introduced as some initial state. We can initialize it with all zero values or some values that we learned during training, and also an input. And these are processed in our model or in our cell, basically, and produce an output. But they don't only produce an output, they also produce another state. And this state is basically given to the next cell and so on, and we can process it and create another output. And what some people always forget, you don't always basically have to give an input every single time. I mean, there are some cases like, for example, labeling an image where you will have one input in the beginning, and then the network will basically just go on and on to produce its own um, multiple outputs till it's finished. But the idea is always that we create this new hidden state, basically, pass it on to the next cell, and it can go on and on. And one important thing to note here is this can have multiple dimensions. And some people will mix that up with a multi-layer RNN, or at least that happened the previous semesters a couple times, but there's no reason, like that's not the same thing. So there are multiple different versions of how we can set this up. Um, we can have, oh, wait a sec, where is? We can have some structure which is called one-to-one. That's basically what we've been looking at so far, where we have one input and one output, right? That's good for stuff like image classification, image segmentation, and so on. We can also look at a task one-to-many, which is what we basically just looked at, which is image labeling. Where we basically have one input, and then the network just produces a bunch of outputs till it finishes at some point. Then we could also think of something like many-to-one, which is good for stuff like sentiment analysis. Like, let's say you have a sentence, you're analyzing reviews. Are reviews good or are reviews bad? It used to be an exercise before the transformer exercise. And you want to label it as a good review or as a bad review. That would be something many-to-one, right? We have one output, good or bad, and we have many inputs, all the words, basically. Then we also have many-to-many. I mean, we just saw it. Video segmentation would be like a classic um, part of this because, like I said, the previous frame depends on, or the current frame depends on the previous frame, and so on, right? And the last version is also many-to-many, but with a slight difference where we basically shift input and output. This is used for machine translation because obviously we have to look at the entire sentence before we can start creating outputs. I mean, just because we can't translate word for word because the order might change in a different language. So we basically have to run through all the inputs, and as soon as we've done that, we can start producing outputs. And one thing some people always ask is usually like, doesn't this model always produce outputs? And yes, the model always produces an output, but we don't really have to put it into the loss, right? We can just basically only look at these outputs, and these are the outputs that we're interested in. Like here, we also produce outputs, but they're not inserted into the loss function because we're not interested in them, basically. And there's also another version, which is called multi-layer RNN. And the idea is here that we basically just stack another layer of RNN cells in here, which each have their own state that's basically transmitted through the cells. And in this direction, we share the weights for like every single model here has the same weights. That's the whole idea of RNNs, right? In this dimension, like in the dimension horizontal, we share the same weights. In this direction, we have different weights, right? So each layer basically has their own weights. And each layer, again, can have multiple dimensions of a hidden state, right? That's not the same thing. I mean, yeah, the last couple of semesters, they had some problems with understanding that. And I think in the slides, it's not always so clear what multi-layer RNNs are and what multidimensional hidden states are. I hope that sort of clears things up. Yeah, so and you can even have different dimensions, like each state, they're sort of independent of each other. So let's quickly go over the math of this so that we can see some of the problems that we have. The idea is that we have this input or this hidden state from the previous cell and a current input. And we sort of process them together using these learnable weight matrices. And these are the things that will stay the same over time, like not over the layer. Like each layer could in theory have their own weights, but over time, these stay the same, right? So we mix our previous state and our current input together to create the new state, right? And from this state, we can also produce our output, okay? And again, like I said earlier, we don't always have to look at this output. Like sometimes it will, sometimes if we're not interested in the first 5 outputs because we're looking at this many-to-many machine translation case, and we're only going to look at the last 5 outputs because that's where actually our RNN is actually starting to produce outputs. So what are the problem with these RNNs? Well, if you think about it, at any point in time, I could have just cut the model off. So I could have just used, like, if I use this initial state here and plug it in as initial state here, it will produce the same output. So this here basically compresses everything we've seen so far, right? So the model will still produce the same output if I just cut it off and use this hidden state and give it on as the initial state. The model will still produce the same output. So this vector here, this hidden state has to compress everything the model has seen so far, all the data, okay? Now, why is that a problem? Well, these things tend to forget. Why is that? Well, let's look at the formulas again. And for now, I'm just gonna get rid of our nonlinear activation function. If we start unrolling our network, so I'm just gonna type in the formula for hidden state of the previous layer, which is according to the formula. We can just swap the indices, and we'll just open up the brackets, and now we can already see what's happening here. We see here a weight matrix squared. We see this multiplication here, and we can do it another time, like for another layer. And now we already see here this exponent is starting to grow and to grow. And this is because we're basically multiplying our hidden state by a weight matrix over and over again. And the important part is basically this guy here, because we already see this exponent here if we look at the previous input. And what happens if our weight matrix is, for example, let's say we're in one-dimensional case, what happens if our weight matrix has values smaller than 1? What happens? That was a question to the class. Exactly. So basically, the influence of that input will converge to zero. Same what happens if our weights are like if are above one. Exactly. So suddenly, like the previous inputs are a lot more important than our current inputs. So ideally, we would want to values around one. I mean, we're not going to be in the one-dimensional case. We're going to be in multidimensional case. So here we're not looking at the actual values in the matrix. We're looking at the eigenvalues. But I'm not going to go into the math of eigenvalue decomposition and stuff like that in the analysis. But yeah, just have this idea of exploding or converging to zero, what this basically means for us. And what we will always also even see these exponents in the gradients, they also pop up there. So they will cause the same problems with learning. Either we will have this huge zigzag motion if they explode, but we can easily fix this problem of this exploding gradients by using what? Like what technique is often used to solve exploding clipping? Perfect. So we can basically just cut off the gradients of a certain magnitude and solve this problem quite easily. But how can we solve vanishing gradients? Is there something we can do? Yeah, it's hard to solve that problem. But what we sort of can do is choose a different model architecture. And this is basically where, long short-term memory units come to play. And I guess you always also went through that in the lecture. So the main difference is um, we're going to be using gates instead of these weight matrices that are multiplied over and over again. And this actually, creates this, we always call this highway for the gradients, but at the end of the day, it means we're not multiplying it with the same weight matrices over and over again, because each gate in every single cell state will be slightly different. So that way we can sort of maintain it. And also we're adding stuff and we're not necessarily multiplying it by these weights anymore. So that's like the main difference. The basic architecture is that we have this forget gate, which basically we run our previous, I would call this sort of like the short-term memory. We run this combination of short-term memory and the current input through a sigmoid function, and this will create this will be a value between 0 and 1, obviously, because I mean the sigmoid function is always between 0 and 1. So this will determine how much of our current input or our current cell state do we forget, okay? Or if it's 1, we will keep everything, right? And the next thing is we want to add something to our memory, right? And this is what the input and cell update basically do. So our input gate basically determines how much of the current stuff we're getting in, of the current input, do we add to our long-term memory, and also sort of how much of our short-term memory do we add to long-term memory. So these two basically run through a tanh function, which will be between -1 and 1. And then the input gate sort of determines how much of this cell update will we actually put into the long-term memory. And yeah, this is basically exactly this function. So this is the previous state, how much do we forget? And this is basically how much do we add to the current long-term memory. And then the last step is we also produce an output and our short-term memory if you want to, which is basically just this function, which only depends on the state here. Okay. And that's basically all you sort of have to know about LSTMs. I mean, here are the formulas again. I mean, that's just from the slides in the lecture. But the important thing is really that we create this gradient, or this highway for the gradient. So instead of having this weight matrix that we multiply over and over again on the state, we just have this gradient that can just flow up here, and we're only running it through this forget gate. But mathematically, I'm not going to write up all and like unroll it, but you can see that it's actually it's not affected as much. But we still have the same problem. Like again, LSTMs are better at like translating longer sentences, but they still, I don't know, I think it was 1,000 words that I read once. That's where it starts to struggle with translating, because it has to memorize like this state still compresses everything it's seen so far, right? So it still has this sort of this bottleneck of having to compress everything and to memorize everything. And they just tend to forget at some point. I mean, it works better, but it's still, yeah, I can't analyze like, I don't know, an entire paper with 10,000 words or something like that. So yeah, these are basically problems. We still compress the entire past in our state. And even in LSTMs, the state usually sort of depends on more recent inputs than on further back. And both models are kind of hard to train or tedious to train because we always have to run through the entire sequence. And we also always have to basically have this loop where we produce an output, given the new input, produce an output, because we always have to wait on the state, right? We can't just run everything through in once and then get an output immediately. We have to have this loop. And this makes training really, really, I wouldn't say difficult, but it just makes it a lot less efficient. So what is the solution? I mean, transformers solve a lot of those problems, and we'll have a look at why. So the first observation that we have to make is context matters. Like the words around a word determine the meaning of a word. Like if we look at the word bank here, the money's at the bank. And if we look at this bank here, the river bank is long. Those are two completely different meanings for the same word. Like they're spelled the same way, but it's something completely different. Okay? So we somehow want to introduce other words and sort of mix them into the word that we want to improve. So one big difference in attention or in transformers in general is that we sort of have this hidden state for every single word. We don't compress everything into this hidden state for the entire words that we have. We sort of have a hidden state for every single word. And in the beginning, this will just be the embedding. Embeddings are basically numerical or vector representations of our words. So if you're unsure on what embeddings are, we can either have a look at the transformer exercise, third notebook, the first couple of paragraphs, or just look online on what embeddings are exactly, or the intuition behind them. But basic meaning is we for every single word we have a lookup table, and this gives us a vector representation of our word. So this will be the initial representation for each single word that we have. And now we want to start introducing context from the other words. So we somehow want to get information from all the words in the sentence and somehow bake them into this word. And now we also want to update this representation somehow. And that's something else that we did in RNNs. And right in RNNs, we created this one hidden state for all our words and compressed it into this one state, and then went on to translation. So here we're going a different route. We're basically creating this hidden representation for every single word at the same time, okay? So we can do this for every single word and slowly update their hidden step. And that's how we're basically going to improve their knowledge of the words around them. But the question is now, like, what exactly is flowing here? And how do we determine which words are more important, which words are less important? Well, let's just concentrate on the word bank for now, okay? What we're going to use is we're going to use this query function. So this query function is basically just a linear layer, right? It's just basically WQ times if this is X. It's basically just a linear function. And what it does is it creates a query from a state, if you want to, or from an embedding, okay? This query is sort of the idea the idea behind the query is what I am looking for. Okay, so what am I looking for in the other words? And they should give me something later on. And we'll do something similar for the other words that we want to compare it to. We're going to use a key function. So this key function, again, is just a linear layer. And from our embedding, it creates these keys. And these keys basically sort of say, like, what do I look like? Okay. And now all we have to do is we have to compare our query with our key, okay? And we'll do this using a dot product. So the more similar what I'm looking for is to what I look like, the higher the score will be, okay? One important thing to note is like these key matrices, they're shared across every single word, right? So we use them over and over again. Like they're not different for every single word. They're the same word. And they're basically, think of them as a function. I give you an embedding and it produces this key vector. And this key vector is basically, what I look like, and for the query, what I'm looking for. Anyway, we create these scores, and these scores basically sort of tell us like how good does this key match what I'm actually looking for. Okay, now, or how good is the match? Next, we have to normalize it. We usually do this using softmax, so all our scores will now add up to 1. This is important so that later on our embedding vector doesn't sort of explode, because if these score values were like wouldn't add up to 1, we would see this increase in growth. Now we'll run, now that we have the scores, we can basically create value vectors from our embedding. So these haven't changed, okay? The embedding vectors haven't changed. We're just going to use a different function. We're going to use a value function if you want, which is, again, it's just a linear layer, okay? It's just a linear layer that creates value vectors. And these value vectors are sort of what I have to offer, okay? Now what we're just going to do is we're going to multiply each value vector by its corresponding score, and then sum everything up down here. And then we create this a new representation for a word bank, which now has information from all these words here, okay? So we baked all the context from all those words into the representation, the word bank. And that's going to be our new representation. So this is basically what we just saw here. We can do this for all the words, right? We'll basically go through all the words and update their representation. And that's how we basically get all the information from these words into bank. And notice also bank is also in here, right? So we also get information, or that doesn't only depend on the other words, it also depends on itself. But one problem that we have with this attention mechanism, if we just did it like that, is what happened, like the river, at the moment the sentence is the river bank is long. But what happens if we switch it? Like the long bank is river. The result will still be the same, because I mean, the value functions only depend on this representation. So these pairs will not have changed. So the similarities will also correspond to the word. And we can always change the order in a sum, right? So the result will be the same. But maybe but this isn't obviously the same sentence, so bank might have a different meaning in this sentence. So how can we make sure that the position in the sentence also has an influence? And we do this using positional encoding. So think of positional encoding as sort of like a bias that that depends on the position in the sentence where we are. Okay, so if index 1, or the first word always gets this bias, the second word always gets this bias, the third word always gets this bias. So now if we would switch the words around, it would change, because suddenly a different word is added to this bias. That way we can make sure that the order in the sentence actually matters. All right, so let's just have a look at everything combined. Like we compare our key to our queries using the dot product. We create these scores. We normalize the scores using softmax. So we have our normalized scores. And then we multiply our scores with our value vectors to create these contextualized queries, where we have the information from all the other value vectors, or all the other words, baked into the current word. And we can also do this using matrix multiplication. So if we wrote all this up, we have this dot product up here, our queries times our keys. Then the scaling here, like over decay, is basically just, imagine if we looked at the scores of a dot product with 10 dimensions versus a score of a dot product with 100 dimensions. Obviously, the score would suddenly grow. And this would cause numerical instabilities with the softmax function. So that's why we sort of want to make this independent of the dimension of our keys and queries. That's why we basically divide by the dimension of our keys. That way we make sure that it's always in a good region for the softmax where it can train properly, and it's also independent, which makes hyperparameter searching a lot easier. Anyway, we get all these scores. So this here produces our scores, this guy here. We run it through the softmax to normalize it. And finally, we multiply our normalized scores with our value vectors. All right. Now, in the transformer, we actually use two types of attention mechanisms. On the one hand, we use a self-attention, which we basically already discussed, where we look at a word and see how it depends on all the other words in the sentence and also on itself. And we sort of need this to basically add context, like from the other words, right? That's what we use self-attention for. And it's usually used in the encoder. We'll get to that later. On the other side, we also have this cross attention where we basically have a different word that's not in the sentence. And we look at how does it depend on other words. We look at translation. We might have already produced the first word in the output sentence, der, which is like the German word. And we look at all the other English words. And the idea here is less to introduce context, but more what, like, given this word, what would the next word be that we produce? Okay, so it's a slightly different meaning of attention in this case. So the idea is here, okay, if I give you der and I give you all these words, what is going to be the next word? That's what we were introducing here. So it's a bit of a different idea, but the mechanism works the same way. Okay. So now let's put everything together into the transform. I'm not going to go into detail here because it's not really relevant for the exam. But we sort of have this encoder and this decoder structure. In the encoder, we have our attention block here that we already discussed, like this self-attention. Only difference here is we use a multi-head attention. What multi-head basically means is we don't only have three weight matrices, like our query key and value matrices, but we do that multiple times. So we create, like for the same embedding, we'll create different queries, different keys, and different values as many heads as we have, basically. So if we have 6 heads, we'll create 6 different queries, 6 different values, and 6 different keys. And then we'll compare them with each other and create 6 different outputs. And then we basically compress it into one output again and go on to the next layer. And this encoder, what it basically will do is it will contextualize the inputs. So it will take all the inputs. Here, this is where we add the positional encoding so that the order suddenly matters. We process it, and now every word knows about the existence of the other word, because here, with our input embeddings, the words still have no idea that the other words even exist. As soon as we run it through the encoder, we basically add all this context to the words. So now each single word knows of the existence of the other and has slightly changed its meaning, if you want to, because yeah, it knows about context now. It knows about verb relationships and stuff like that. So we basically just process the inputs and make sure, yeah, that they know of each other. That's the job of the encoder. The decoder, its job is basically for every word that I put in here, give me the next word that you would produce. So if we would start with, I don't know, with the start token, for example, it would try to produce the first word in the sentence, ich. Then we would continue this. We would give it 2 words basically down here, start and ich. And given those words, ich, it should produce the next word, ich bin, maybe, and so on and so on. So as many words as I put it in the input of the decoder, that's how many words it will produce, shifted left or down here shifted right, depends on how you see it. And it will produce the next word given a word. So for every token, it will produce the next token. And this will depend on the words it already has produced and also on the encoder value. So on the inputs to the model that we basically looked at. So on the process inputs from the encoder, but also all the previous words that we've already created. So bin obviously depends on, well, the start token, but also on ich, because it's the next word, right? And for this reason, because we don't want ich to depend on ich, right? Otherwise, that would sort of be cheating. That's why we need this masking here in the decoder. And this basically makes sure that the first word only depends on the first token, the second word can depend on the first and the second token, the third output can depend on the first, second, and third token, and so on. So otherwise, we would sort of break causality if you want to, because ich could depend on the output that we've already created. Yeah, but this isn't that important for the exam. We just wanted to sort of go over it again one more time. But the important part is really that you understand sort of how the attention mechanism works, so that we're basically comparing these these queries. So what I'm looking for with the key values from our embedding that we create using these weight matrices, right? And as soon as we get these scores, we can incorporate the value vectors into our updated representation for each word. All right. Are there any questions on those couple of topics? Yeah, I mean, if you sort of have an idea of this encoder-decoder structure, that's awesome. But you don't really have to understand like the exact insides of the transformer. But the attention mechanism, yeah, as Dan said, and positional encoding and stuff like that, that is important to know for the exam. To just understand this concept of having keys and queries. Example where you would use multiple RN. Well, I guess the more complex a task is, in a way, the more layers you would sort of ask, because each layer sort of has its own dynamics inside. So you can obviously create a lot more complex tasks or a lot more complex behaviors. So again, it's out of the blue. I can't really think of it, but I guess you could use it for, I don't know, if you're doing some kind of an image, some segmentation on videos or something like that. You would just create this more complex model that has, yeah, you can just learn a bit more. Do we have backprop with multiple layers? No, we definitely don't have to do backprop with multiple layer RNNs. That's not something, and obviously there is back propagation in that to learn, but you don't have to know the formulas and stuff like that for the exam. In the decoder, emulate the current output word to the encoder representation of the, yes, we use cross attention in the decoder. And basically we want to predict the next word given the input, right? So in the decoder, there are actually two versions of attention. We have this causal attention, where like given the words I already produced, create the next word for every word, but make sure it only depends on the words I've already predicted, right? And not the future words. So that's this causal attention, which is also a form of self-attention, just also has these masks. And then we also have this cross attention where we bake the embeddings or the input from the encoder into our prediction, because obviously what we want to translate also depends on what we have to translate, right? I hope that answers it. Basics of diffusion model. How far should we go into it, Dan?
I mean, I'd rather focus on stuff that's actually relevant for the exam. Are diffusion models relevant?
Once I'll just have a look at the current.
More relevant is to not how diffusion works, more the architecture that it uses. For example, we have two different. One is using an autoencoder to basically diffusions. The most basic idea of diffusions is to denoise an image. They use it to generate new data, which is what an amazing idea. But it could work either with autoencoder, so to take an RGB, add to it noise, and then encode and decode it to denoise it. Basically, right, like where you could add just random, like in a data augmentation, random black and paper noise, or you could do it already in latent space, and that's what you need to know. Like to think what could be better, what is the advantage of here and what the advantage of doing that. That's all you need to know. Besides that, all the mathematical background of diffusion is irrelevant. Markov chain, for example, for reinforcement learning, also irrelevant. Graph neural networks, irrelevant.
I mean, I would actually almost put it the other way. There are some questions for some reason. I mean, if you've done the older exams, you'll see this one question type that often pops up with convolutions or with yeah, finding out the respective field. And that's something that for some reason isn't in the lecture, but is always in the communal notes and in previous exams. So that's maybe something you could have a look at. But I would say it's if you understand the entire if you understand the communal notes, you're already pretty good. I mean, I haven't had looked at the entire recent draft, but I guess everything that is relevant should be in there, right?
Yes, and also we've updated most of it like in the past few days. For example, thanks to Benjamin. So if you follow the lecture notes and know to solve all the questions that appear there, you're more than prepared for the exam. Also, of course, to solve the previous exams, to practice a little bit of backpropagation and stuff like that. But besides that, like I think that if you decide not to follow to read the slides, which I find just not informative enough, they don't really cover anything in depth, to just say buzzwords. You can definitely do that, and you'll be just fine. Autoencoder in the slides is a FCN, but full. Okay, again, QFF, FCN. FCN could be also translated to fully connected network. So like there are so many names, so I wouldn't say FCN is a fully convolutional network or fully connected network. Say their full name, because you're saying it's FCN but full of FC layers. So fully connected network does full of connected layers. So I also, for the exam, for inconsistencies, autoencoder in its definition is fully connected. And then we can say that it's fully convolutional, and we call it UNet usually.
Can you repeat the difference between self-attention and cross-attention again? I mean, it's not really relevant for the exam to know like this deep about self-attention and cross-attention, but the basic difference is in self-attention, we're basically looking at one sentence and all the words in the sentence and related to the words in the sentence itself. And this is basically how we introduce like knowledge from the other words into this word, right? So we contextualize it. So the river bank is long. Bank now also knows about the existence of river and sort of changes its meaning. Okay, that's self-attention. And cross-attention, at least where it's used in the decoder and the transformer, is we're basically comparing two different sentences to another. Okay, so we have this English sentence that we want to translate, and the word that we already translated, and we sort of want to figure out what is the next word after this word. So we compare it to all the words that we see in this English sentence, and that's how we can create the next word. So this is the idea of cross-attention, where we have attention between two different sentences. And here, like I said, the idea is less to add context to it, but the idea here is more is to create the next word, because that's at the end what the decoder produces. It produces, for every input, it produces the next word given that input, and also the encoder inputs that have been processed. I don't know, does that sort of answer your question, Elisa?
Okay. If we have the time and we don't have any more other questions, would you mind walking us through a solution of the multidimensional derivative backprop stuff step by step?
Yes, I could do that if you want. But for that we will release Julius. If so, is it any other question about RNNs, LSTMs?
Only if we haven't covered anything that is relevant right now.
I mean, we've basically gone over everything that is relevant for the lecture on RNNs, LSTMs, and so yeah, basically for LSTMs, you want to sort of look at the architecture, like how How are they set up? Yeah, sure. I can share the slides. I mean, it's basically just pictures, but yeah, sure. I can share them. But yeah, so LSTM's basic architecture. Why do they sort of work a little better than RNNs, and what are the main components of LSTMs? So that's what you want to look at for LSTMs. You want to have a short look at, yeah, basically about embeddings. What are they? What are they used for? And some problems of the RNNs, like what are typical problems that we face with RNNs, and also with LSTMs, like what are the problems and what do they solve? I guess both things are important. And for transformers, like, yeah, you want to know how the attention mechanism works, and also like a bit of the intuition behind it of, yeah, having these query keys and values and what they sort of represent. And then you should basically be set up pretty nicely. Yeah, so if you know the gates and what they're used for and how they're sort of set up, then yeah, that should be more than enough for the exam. So yeah, basic architecture of LSTMs, and maybe some pros and cons. Doesn't hurt to know. What are they good for? What are their limitations? What is relevant each backpropagation over the computation? Which matrix does Jose mean?
Yeah, that's what I'm wondering.
The question relevant to which things are important practice speaking. For example, much of the exam is basically responding theory things. But for example, if they put you like something like if we have like a computational graph and we have to backpropagate over it, that's a practical thing. So it's like, that's my question. Which things are relevant for a practical relevant?
I think that the best practice, I think it is in 2020 summer semester 6D. That's the question. I already posted the answer on Piazza. They also posted it in the updated yesterday the exam. There is a question about backpropagation through RNN, 2 steps through RNN. So it's not that difficult. I think it in an exam that was so really difficult to do such a thing. So, but I think it's just a good practice. To have if you want to do backpropagation to understand how it works, to do the chain rule, that's a great practice question. Of course, there are others in the exams, for example, in skip connections or whatever, or also in the mock exam you have, or I think last semester there was also something. So that's a good idea. I think that like last semester we had backpropagation through a convolution. I think it's just good to do that just to understand the concept. It will not return in this exam. It's just a two-part question to do in an exam. What aspect topics from practical exercise? You mean like the course exercises, like exercise 1 through 11? Everything is important. For example, exercise 3 talked about datasets and data loaders, and like how do we pre-process data, and when do we apply data augmentation, and to what to do that, and how to split the data. For example, like that. The exercise 4 discussed mostly to do backpropagation through a fine network, which is really important. And as people asked here, we will do it now to understand how to do multidimensional derivatives. Exercise 8 was autoencoders, really important to understand autoencoders and why do you use them for, what kind of machine learning practice is that, supervised, unsupervised, like it's all the thing about transfer learning. Exercise 10 discussed semantic segmentation. So what's the difference between classification and semantic segmentation? What does it mean about the number of the number that we divide the loss function by? What is important between the input and the output between the semantic segmentation? How would they change a network architecture to fit, for example, image reconstruction to semantic segmentation? So everything that was in the exercises is important. That's something that we expect you to know. Coding specificities, no, definitely not. You should be able to read like PyTorch syntax. So if, for example, we defined a network and I give you conv2d and then input channels, output channels, you should just know to be able to read that. And you're not like, oh my God, what is this? What is the advantage of LSTMs is that you use gates to remember forget information, which allows to have no. So the thing is, about LSTM, I think it would be nice to have the visual again.
Yeah.
But anyway, so LSTM, the cell state, this I can also I think do it from my computer. I can just.
I mean, you have the same slides.
Yeah, I think I have it open. Here it is. LSTM.
It's just the slides from the lecture right now.
Yeah. Oh, I posted it. Nice. Anyway,
convolution update from last year. Do you mean the backpropagation through convolution, or what do you mean? Yeah. I don't know.
I think that's what they meant. Yeah, the convolutional question from last year. It's irrelevant. It's good practice. Irrelevant for this exam.
It's definitely irrelevant. I mean, I already did a Piazza post on that on how to get on how to backpropagate through convolutions. I think I'll just look for it for a sec.
Yeah, so basically in that exercise you had to grow the matrix from 3x3 to 4x4, something like that, and like overlapping the filter with itself to grow the matrix to 4x4, and I didn't understand that.
Honestly, I don't have the entire exam in my head anymore. Which problem was it?
So it was in the convolution part, you first had to do like a normal convolution with a filter and an input, and then you had to like find the derivative of the filter with respect to the input, I think, or something like that, and you had the upstream derivative.
Yeah. Okay. Yeah, but I don't think you had to. Did you have to increase it? Wait a sec. Oh yeah, you did have.
I think you wrote the solution on Piazza, and we also have the solution.
Yeah,
we also have.
I had a look to the solution, but I didn't understand why we are overlapping this matrix. I mean, it's an operation with matrices that I had.
I can go through it if you'd like. I can explain it if you'd like. I can open it. But first, I want to answer the first question that I was asked. Advantage of LSTM that it gets. Okay, so remember the forget gate that we see here. I don't know if you can see my mouse. So basically, this is a sigmoid, and the sigmoid sends numbers between 0 and 1. Now, we multiplied the previous cell gate with this forget gate, or the output of the forget gate. So those who get 1 will just pass through completely, like with full magnitude. Those that are 0 will not pass at all, and some of them will be in the middle. So that is, so for those who have 1 in this state, in the forget gate, they have full magnitude of gradient. Because this is just multiplication, yeah. That is not the sigmoid. The sigmoid, the gradient problem of the sigmoid is just to the input of it. And then you have also a plus, which is also just a skip connection, and it has full magnitude of gradient. So those who get full mag gradient have this high grade of gradient. But as Julius said, it still suffers from very long-term memory because some of the information will be lost as we go from one state to another, but still much better than RNN. I
just uploaded the Piazza post. I don't know if you want to just open it. Maybe it's easier.
Yes, let's see. So that's the question for those in the previous semester. For those who don't know, we had, I think we had a matrix, right? I think the input matrix, and then we had.
It's everywhere down in the
here. right? And then we applied a kernel to it. Okay, so basically just did a convolution, a kernel, I think, with what, stride 1 and no padding. Yeah, basically. So you got 2 on 2, right? The result of the forward pass was that you already just explained this. So the result of the forward pass was 2 on 2, something of this shape. Remember that remember that the gradient of a matrix in the neural network with respect to the loss function has the same shape of that matrix. So basically, we have 2 on 2 as the upstream gradient to this layer. And what we needed to do, remember when we apply a convolution on a filter, for example, let's do annotation with my mouth, which is fun. So the first window would be this. The second window would be this. Third window is this thingy. And fourth window is this. Okay. Now, remember that the derivative of we want the input, right? The derivative, if it's xw, that's what we do in forget the bias for now because it's irrelevant for the derivative. And so xw is the function that we do also in affine layers and convolutions. It depends just on the window that we're looking at. And so basically the derivatives, especially in contrast to fully connected layers, that's what we will do next. In convolutions, we do dot product. Dot product is element-wise multiplication and summation. So each instance in the input is applied with one weight, and then we sum them all up. So in contrast to fully connected layers, where the matrix multiplication works with rows and columns, which works a bit differently. Okay, so we remember that the derivatives of the x's in each window, for example, the pink window, are simply the weights of the kernel. The weights of the kernel. Okay, so that we see here. It's not gonna be nice because it's not gonna stay. And I'm gonna clear my drawings. So basically, it's gonna be them. For each one of the windows, for example, let's talk about this one, it's gonna be these multiplied, because it's the chain rule, with the relevant upstream gradient. So for the first window, it's gonna be multiplied by the respective upstream gradient. We will take this matrix and we multiply it by 3. Okay, so that's what we did here. Remember that we're still talking about all the x's. We're doing the derivative of the x's. The gradient of x from L has the same shape of x. And we're simply summing for example, for x11, where they corresponded or in calculation. So x11, to do that, we can just plug in, as Julius really just showed here, at each point of the matrix. Okay, so we can just plug them in and sum them up. So we basically just put them in. So we multiply, for example, the kernel with 3 and plug it in the right place where the x's came from. And then we go one window, we'll multiply the kernel with -1 and plug them in the right place again and again and again, and we just sum them up, and that's what we get. Now, it's not an easy question at all to do in an exam, definitely. But it's good for your understanding how these kind of things work. Any questions about that? I can also, because I have, I'm not sure if it's here. Let's see. Unial nodes, derivatives, recap nodes, or it will be an overlist. Here, con backup, I can just share with you. We have it also here. So here I have it with colors, if it helps in any way. But I think that Julius' answer is good enough. We don't need also this. Any questions about that?
I mean, you said you explained this simply for completedness, but we're not doing backpropagation of convolutional layers in the exam.
No, we don't do it.
Okay.
Yes. The high grade of gradients, you can expand one from first term to second term with identity matrix. Yeah, okay. So Eunice, you want to share, I think in page 65.
Like I do understand how you used the chain rule and kind of added these two parts together, but I don't understand how this implied that we multiply the derivative of L with respect to xl plus 1 with the identity.
Okay, you're talking about skip connections in the lecture notes. Okay.
Yeah, exactly. Like, how does this imply the full magnitude of the gradient? The first expression. Like if we want to mathematically show the highway of gradient.
Just a sec. Let me go there. Popular architectures questions. Okay, 65 would be, maybe it's 65 already in the previous version. No. Perfect. I'll just send it here. Share.
But I guess I'll take off, so I have to go to work.
Yes, Julius, thank you very much. Okay,
Yeah,
I think
no
I could
worries.
also just, yeah, I'll keep recording anyway.
All right.
So,
bye, guys. Good luck.
Bye, Julius.
Thank you. Bye.
Excuse me?
Yes.
Are we getting this recording on Moodle?
Like YouTube, yes. You'll get it on Piazza.
Okay, the recording of this lecture.
Yes, what we're doing right now.
Okay.
It's still recording, I
Thank you.
think, yeah. Okay. So what we're talking, so what the question was, how to show mathematically the highway of gradients for skip connections. So guys, I'll just do the explanation and then I'll tend to the chat to see the questions, so don't worry. Okay, what is the highway of gradients in skip connections? It's simply that during backpropagation, inputs have like a full magnitude of upstream gradient. That's what it means. Instead of just going, for example, from this place to here, and let just me annotate, from this thing to here, through those blocks, meaning, let's say that they have sigmoid inside, just to the extreme case, so the gradient will just diminish or vanish throughout them. Instead, it has full magnitude of gradient, meaning it will basically, if this is it has an upstream gradient, L over X, L plus 1, multiplied by 1, instead of being multiplied again and again and again and diminishing. That's the highway of gradients. That's what it means. Now, in order to show that mathematically, we simply take, so it's quite simple. We say, okay, we want to show a XL plus 1. Remember that in backpropagation, I know it's not easy for you to see, of course. But remember, in backpropagation, we always look at the abstraction. We never care about other layers in the network. We always care only on what we're seeing currently. So I don't care what happened before, and I don't care what happened after. I only care about this thing, the input and the output to my layer. Okay, so when I want to do the derivative of L in corresponding to XL minus 1, I know the indices here are weird, but just follow them because this is how the image was given. I know it's supposed to be here. So for Lx minus 1, I can simply do derivative of L on X L plus 1 multiplied by the derivative of xl plus 1, the derivative of xl minus 1. Okay, so this is the upstream gradient that I assume through the abstraction that it is already calculated because we calculated in different steps. In previous steps, we already calculated it. Now it's about time to do this layers backpropagation. So we use the chain rule, and we all that is remain is to do this and multiply it in some fashion with the upstream gradient. Okay, so what we care about is simply doing this thing. Okay, what is the gradient of L plus 1 and XL minus 1? Is simply XL plus 1. Now let's just forget that there is also an activation after doing the plus, but there is an activation according to the default definition of residual block. So XL plus 1 is XL minus 1. Oh, I always do that. L minus 1 plus F. This is F of XL minus 1. Okay, so the derivative of this according to this is 1, right? Or if you want to do the full one, it's gonna be it's hard to do it with a mouse. Very hard. Okay. Okay. Now I don't care what I don't care about this. I don't care. All I care is to show that this is 1. And of course we have the upstream gradient. So I'll just call it the out for now because it's easier to write. Plus whatever that is. You write this in the exam, you get full point. Okay? There's nothing here. That's 3 steps. Only 2 steps. Any questions about that?
I still don't fully understand how, like, what made you, like, if you look at the expression purely, like the derivative with respect to L and derivative with respect to XL plus 1, and then you add it to another expression, and then you say that equals the multiplication with the identity matrix plus whatever. How do you, like, why do you say that this is equals this? Yeah, you know what I mean? Like, I don't know if I'm asking the question properly, but
identity. Where is the identity? The identity, like that we talk about skip connections, it's this, that this could learn to do 0, and then basically it just moves past, it moves the same thing. If I don't see the word identity, but when we say about skip connections, that identity, we talk about this one going to 0, so it just goes from here to here, and they're equal.
oh, sorry. Then I meant the multiplication with 1.
Yes, so that's the point. So this one is is XL minus 1 derivative by XL minus 1. Because XL plus 1 is XL minus 1 plus F of XL minus 1. And I want to define the derivative of this according to this. So I simply take the derivative of accordingly. So this according to L minus 1, and this across to L minus 1. And this across to L minus 1 is simply 1. It's the same variable.
Oh, okay. Thank you.
Okay, so, and that is the highway of the gradients. I will fix this. I think it will. I have a better annotation to explain it better, so it's less confusing than what you see here. Okay. So, any questions about this question, or I'll read what's going on in the text in the chat.
Just to summarize, mathematically, we basically just need to write down dl divided by dxl minus 1 equals dl divided by dxl plus 1 times 1. And we can omit the other stuff.
So I do want you to show that because it's not gone.
Okay.
It is important that you show that because that's not true only. But it's like what I did here. This is more complicated than it should be. It should be even simpler. If you want, I can do it now, but I think it's irrelevant to just hold you for me writing LaTeX. What you should know is L xl plus 1 equals L. That's minus 1, yeah? That's what I want. Derivative of xl plus 1 multiply derivative of x plus 1 L xl minus 1. Ooh, that's so hard with the mouse. And then that equals derivative of L xl plus 1, opening parentheses, derivative of xl minus 1, derivative of L x minus L minus 1, plus the derivative of f x L minus 1. XL minus 1, and then only that other thing that this equals to the same thing. I'm just changing this to 1, and that's it. That's the solution. Yes, the multiplication of DL is element-wise. Yes, why is that? Because this is an addition. Okay, it's like addition because the operation that created this is an element-wise operation. That's why the derivative is also like with activation function. What we're going to do right now with multidimensional derivatives, we will see that with activation functions, it works element-wise. And with fully connected layers, which are fine layers that work with matrix multiplication, the derivatives are also going to be with matrix multiplication. That's a fine rule. Other questions that we have in the chat. How do data and batch norm help training faster? So batch norm, what it does, it keeps magnitude of the numbers intact. Numbers do not explode. Numbers do not go too small. The magnitude of the numbers as we go down the stream of the network are going to be in some meaningful magnitude, so that the weights will have meaningful gradient magnitude. And simply, it's also easier for the network to learn. That's already much deeper and abstract idea of what neural networks are and how they work. But each layer tries to learn some kind of distribution of the input. So if you change, for example, the normalization layer, you train your model, and then you decide to train batch norm and group norm, the network expects the inputs to it. Each layer would expect the input to it to be something else of different distribution, and it will not perform as well. It will have to retrain. So each layer expects some kind of distribution, and this one is quite easy to learn. Usually, this follows a Gaussian. So that's why it makes it much easier and faster to learn. Much less optimization problems, because there is the theoretical mathematics and there is the applied mathematics, and we're dealing here with applied mathematics where we can have lots and lots of numerical problems. One more question related to transformers. Why is in the exercise session we don't use bias in QKV? I think that actually I don't know why. It's usually in transformers we don't use bias in the linear layers. It's a great question. I don't know how to answer that. In residual blocks, if block works bad found by if the block then the weight will be learned to be 0 automatically. That's what the neural network does. If it, of course, there are no bugs. And the neural network has a single goal in its life, and it's the reduce the training loss or the error on the training set. That's all it wants to do by course, overfit into the training set. If it doesn't use a residual block well, and it doesn't help it to reduce it, it will reduce those weights to 0. So when we get asked about normalization, it's all about meaningful magnitude. Gaussian distribution helps learning faster. Yes, that's good enough answer. What about we use ReLU to grad and still vanish to small weights. So who wants to answer Q's question about ReLU, gradients and small weights? Just copying it, okay? Okay, yes. So first of all, ReLU does not, as Christoph said, does not suffer from vanishing gradient. It can suffer from dead ReLU. Okay. From the dead ReLU problem. The dead ReLU problem is a problem where an activation of a neuron is negative or not active before the activation. The logic of the fully connected is negative, and then it's activated by ReLU, and then it gets sent to 0. It means that its gradient. Remember that the gradient to the weight of any network is the input, and then the weight of every layer is the input. So if it's 0, it will not get any gradient. Now so that happens, but it doesn't mean that it will happen in every iteration, because a weight in intermediate layer is affected, or not a weight, an activation in intermediate layer, the output to the intermediate layer is affected by many layers before it. So it doesn't mean that in the next iteration, a weight or an activation will also be sent to 0. However, in some extreme cases, it does happen, and then those neurons never learn. For example, without Xavier initialization, that actually happens in deeper networks, because the variance of the numbers just drop exponentially. I think Backprop keeps multiplying the weights down the stream layers when it could be small. Yeah, but it's irrelevant of the ReLU. The ReLU actually gives you, for positive numbers, it gives you full magnitude. So the ReLU does not cause this problem. It doesn't cause vanishing gradient. It causes other optimization problems. Any other questions, or should I do multi-dimensional derivatives? First, we only have positive activation. ReLUs near the input of the model suffer less. And I would say that even more, but it really depends on the activation of the initialization. ReLU is linear, right? Oh no, definitely not. The max argument is not linear function. So max pool, for example, could be used to is a non. For example, if I ask you in the exam and it's in the lecture notes, what is an advantage of max pool over average pool? Okay, I want you to give me that. One disadvantage of max pool over average pool and one advantage. Can someone give me that? ReLU simply doesn't solve the problem. Okay, I'm going to write it in the chat. The question: state one advantage and one disadvantage of max pool over average pool. So Nico, you were right, but wait, I'm missing it. But just make sure that because worse than dead ReLU. Okay, but why? Because in the worst case, it actually kills 3/4 of any of the input entries, nonlinear uncanny gradients, reduced dimensionality disadvantages. So advantage is not reduced the dimensionality. First of all, it doesn't have to reduce the dimensionality if you use 311. Remember that we've said it a few times in the lecture. It's important because it was last year in the exam. It doesn't have to reduce the dimensionality, and it's not an advantage. Like my average pool also does that. Loss of information during backprop. What do you mean loss of information during backprop? That's simple. You must be more precise. It kills a lot of the gradients. Max pool disregard information that may be important in making the information. But okay, it disregards information. It could also be because average pool also compresses data, so it's also lossy. I don't think it disregards. It does feature selection instead of averaging them. Not sure that it's a bad thing. Average pool can be considered linear. Yes, average pool is completely linear. It's only just taking the mean. That's a very linear operation. So very good. So do we want to do another thing to discuss another topic from the lecture notes, or I'm going to do the appendix? Let's do clear all drawings. So Katerina is asking, could you please explain again what R in the 1/R term in CS loss mean? Yes. Who wants to explain that? Okay. Yeah. Nice. So the biggest disadvantage of max pool is that let me just go there. Max pool. So max pool, yeah, as you could see, for example, in this example here, it takes only the maximum value of each window. That means, and the gradient of the maximum value would be 1. The gradient of all other entries in this input are going to be 0. It means, for example, in this case, where there in each window there are no identical numbers. So 2 of them, for example, both of them were 17. So both of them will get gradient of 1. It means that 3/4 of all entries will get gradient 0. That is horrible. R is the number of residuals, number of instances in the batch. So, Katerina, do you understand that answer? What are the residuals? Residuals are every two scalars that are reducted from each other. That is a residual. In image classification, each image has a single value that represents its class, its label, and we have a single value that represents our prediction. So there is 1 residual for each image. So the number of residuals is the number of instances in the batch. But in semantic segmentation, or in exercise 8, when we did image reconstruction, we had residual for each pixel for each image. So it was the number of image in the batch. So R was the number of image in the batch multiplied by H, multiplied by W, and also multiply for image reconstruction, that would be by C. For semantic segmentation, it would be just this. That's actually a good exam question. So it is fair to say that average pool gives us good or better gradients than max pool. I think yes, that it gives us. Now it depends on the kernel size. If the kernel size of average pooling is like 10 by 10, yeah, 10 by 10, what is the magnitude? What is the gradient at each inch we will get? Who can tell me? Exactly, 1/100. That's quite low. Remember that the maximum value, maximum gradient value of sigmoid is quarter, so 0.25. Here, it's like much, much lower. So I wouldn't use any of them, to be honest. I would just use convolutions. Unless you're really, really restricted with. Because also with convolution, you can introduce nonlinearity while applying convolution and some activation functions. No feature selection in average pooling? There isn't. But, you mean like when using go to go down? No, apparently it's not as good. Honestly, I can tell you. From my experience, it simply doesn't work as well. It's a great idea, and in inception layer, that was interesting to introduce it alongside other things. But who says we need to do feature selection? Who says it's a better idea than using them all in some meaningful way? Any other question about lecture notes, or we're going to do, because I think that it was asked before, but it will take some time to do this part of the appendix to do multi-dimensional derivatives. Here we go, and we're gonna just do this thing. Yeah, you could go to Piazza and go to lecture notes and previous exams and just click this link. It will open up the shared LaTeX thingy from TUM, and then you could just, it will compile. And Nicholas, pay attention that your link might not work because it has to be something that I share. But you just do the download PDF and you get, it's the best way to do it because we've updated this thing like multiple times in the last few days, and we will keep updating it. So just to get it every time you want to start working, just go here, re-download it, and you'll have the newest versions. Okay, so should I do this, or do we have any small questions before? Because that will take some time. Yes, Nicolas. Speaker. Sorry, I had some problem with it. Oh, just a sec. Okay, I'm just stopping the recording for a sec. I have a problem with the. Resume recording. Okay, so should we start doing this? Yep. Okay. In order to do that, I think. Let me just. So let's do stop share for a sec. Oi. I'll just crop it. Just not sure it worked. Smart select. Here we go. Okay, let's do share. Samsung notes. A new note. Boom. Okay. Zoom. Share screen. Start now. Okay, this thing. So basically, what the idea of this is to be able to know, given an affine layer, which is y equals xw, is how to find the gradients. I don't care about the bias now because the bias is simply the same thing. It's just not connected because they're not multiplied. And how to find this. Given some loss value, which is always a scalar. Remember, it is always one scalar, no matter how many loss functions we have, how many regularization terms we have, how many whatever, it's always a scalar. And then by some variable, it's a x or the derivative by w. How do we find them? Okay, because apparently it's not, this one is not w and this one is not x. So how do we do that? Once we manage to understand this, we will manage to find everything. So let's just start with the first one. We have, I don't know if you could see well, we have some input. Okay. So first of all, we want to show the sigmoid, but I will do it later. That will be the second thing. The first thing I want to do is just to do the regular one from the beginning to the end, to the finish. So we will first do the forward pass. Forward pass of y equals xw is, I think, correct me if I'm wrong, is this is 0, this is 1, right? And this is 0, this is 1, and this is 5, and this is 5. Right. Then the loss value, okay. And then we apply the activation. Remember that we do replace the sigmoid layer that we had here. We did an affine, now sigmoid layer, then loss. So the activation is just taking element-wise multiplication. What I don't often get is, why could we want to find the derivative in respect to x? That's a great question, Salam. And I think that everyone here has asked it themselves. But that's true because we're dealing with neural networks, which have different cells. And so this is a layer, an output. This is a fully connected layer. So we have both xw here, and x is simply this, and this is the output. So in order to do back propagation and to move to the next layer, we have to find the gradient of x. The gradient of this thingy, the very first x, are irrelevant in most cases. In in style transfer, for example, when we change directly x, that is actually relevant. Okay, so let's just do the second step. The second step is to apply that by to a power of 2. So we have 1, 1, 25, 25. What is the loss function? The loss over this f of y equals 52. Okay, loss value is 52. So questions about this so far? Everyone that tried to do it got to this number. Okay. And as you see, we did a scalar. So, okay, now we need to do L over F. Now, why is the loss the sum of the activations? Because that's what I defined here. I just wanted to take the most easiest, like, yeah, just the easiest thing for you to practice. Like, it would work the same. So we want to do L over F. Remember that it's easier to think that this is a function, this is a number, okay? Always, numerator is function, denominator is some number variable that we want. F here doesn't represent a function, it represents something, for example, I could say that this equals Z, okay? Z equals f of x, and so I could just write, if it's easier to you to understand, that this is Z. It's some variable in that I want to find the derivative of this function accordingly. L represents, I know L, we said it's a loss function, but here it represents, it's a loss value, but here it represents the function that gives this loss value. For example, L could be loss, okay? So this one is this loss function, according to Z, which Z's currently he is Ry, right? So okay, here I think we have a problem, because that's not Y, that's supposed to be f of Y. That's, for example, a mistake. So we want to find the derivative of L over F, again, a number. So F is basically the input to the loss function, right? That's what we're doing. Function according to its input. So if L is, if this is, for example, we said, right, that this is 1, 1, 25, 25. This is F11, F12, F21, and F22. So basically, this is F11 plus F12 plus F21 plus F22. Okay, the derivative according to F. So how do we do that? Now, that's a great question. Let's start with every step. We're going to do the exact same thing. Okay, I want to do according to F. F is a matrix. In order to do that, because all I care is to find actually the derivatives according to these scalars that are independent on the others, they're just assembled in matrices, we start doing them one by one. So we first find the derivative of L over F11. So we go to the function. Yeah, it could be done as F11 plus F12 plus F21 plus F22, derivative by F11. What is the derivative here? 1. So we're going to plug it here. The derivative of the other one, of F12, is 1. 1 and 1. So the result of this formula, or what we, since loss is always the sum of loss for every residual divided by the total number of residuals, irrelevant of what we divide here. Also, I didn't divide. It's just a simple. I didn't even divide here. Okay, we didn't. It's just, this is how the loss function is defined, without any division or anything. Okay. So this one is the result. This is the first one. The first one is 1, 1, 1, 1. Okay. Any questions about that? How we got to L over F? How how we approach this? How we look at denominator, denominator?
So, one question. If F was defined as the sum of x squared,
F naught,
then,
F naught is not a sum, it's L, yeah? Or I didn't hear you.
Yeah. So, but if F was defined as the sum, could you do it?
Yeah, okay. So if F was the sum of x double, like the input, right? F of x is the sum of all the inputs inside.
Yeah.
So basically, L would have taken f of whatever, yeah, and it will be just a single number, right? It will be just a, if this is z, it will just be this in this case, yeah.
Yeah. Okay.
And it will be just 1. What also helped is because we are dealing with scalar loss function, the derivative will always have the same dimension as the input. That's true. So remember that if f of x is of 2 of 2, the derivative is also going to be 2 on 2. So now we're going to do L over y. Remember that y is the input to f. Okay. Remember here this is the number, here this is the function. We want y, we want this that went. So again, and remember that this was an element-wise multiplication, element-wise operation to do f. So f applied element-wise on its component y. Basically, f of y equals y11 to the power of 2, y12 to the power of 2, y21 to the power of 2, y22 to the power of 2. Okay, that's all there is here. This is the upstream gradient. So all we need to care about is this thing, and to find this. What are the derivatives of and remember that y, if I remember correctly, it was 1515. Okay, that was it. So that's all I need to find. What is the derivative of each one of it, if each single one of them? If I do this, what is the derivative of this? It's 2y11, 2y12, 221, and 2y22. Okay, so basically this one equals 2, 2, 2, 10, 10. Okay, so this one okay, another important point. Because f worked element-wise, this thingy is element-wise. Okay, so basically, so the final thingy is 2, 2, 10, 10. Again, y was also 2 on 2 matrix, so the derivative is 2 on 2 matrix. Okay, I want to explain another thing, so to make it clear. So the derivative of L over y equals the derivative of L over f, the derivative of f over y. We want to find, so we said that we want to find the derivative of L over y11, the derivative of L over y12, derivative of L, y21, derivative of L, derivative of y22. That's what we wanted to find, right? We found it, that's what we wanted to find. As I said, we want to find each one independently. How do we do this? So we just divide and conquer. y11 equals the sum over divided of f okay, we can do this. I equals 2, j equals 1 over 2, fj multiplied by f ij over y11. Why is that? Because we want to take all the entries of f and to think how are they affected by this thingy, okay? Because y is the input to f. There's no sigmoid here, but yes, sigmoid is always element-wise. There is check one. Activation functions are all element-wise, if I'm not wrong. Okay, who can tell Nicholas which activation function we know that is not element-wise? Softmax, very good. But isn't, of course, so it's just a little anecdote. Very nice. Okay, so that's what we want to find. Okay, and now we start. So what I did was basically the visual trick of doing that. Okay, in the paper we said, okay, let's just do the sum with a visual trick. So I'm just putting all of these L over Fij, which I already know what they are, right? We just found them because this is it. This is F11, this is L over F12. I just don't want to write it because it just takes time. Okay, and we're doing this thingy. F11 over Y11 and F12 over Y11 and F21 over Y11 and F22 over Y11. Okay, I'm doing this the Y step just again to show you what we did in the article. And then we do dot product. Dot product is exactly like how convolutions work, is element-wise multiplication and summation of everything. So I add them up. Okay, basically we just need to solve that. So F11 over Y11 is 1. Or true, that's not true what I just said. It's what we did. It's not 1, it's just what we did earlier. It's like 2Y1, okay? And which we have to also implement to put the Y1 in, so it will be the 2. Yes, and this will be 0, and this will be 0, and this will be 0, and this will be 0. Okay? And then we multiply them, and we get 2 eventually. Multiply and sum. And we do that for each one of them. And we get the final result that we got here. Okay? But we do it separately for each one. We could just find a better way to do it. The first way I did it was easier, but this is just for you to understand. Do we have enough time to doing all of this? Try to do that yourself. I think in the first method that I showed, what I did right now is to go into very, very deep explaining how each step works. You don't have to do all these steps. Now we will do the easiest part, okay? So we know that so we need to do L over X. That equals, again, L over the function that creates that X is part of. This is the function. And now it's a value, it's the input to L, of course, but now it's the function to X. Okay, we've already seen in the article, we've explained, this is recorded, yes. We've already seen in the article how to do it step by step, but now we've seen that there is a trick that if Y equal XW, and I want to find according to X, I replace X with the D out. This is the D out, and transpose the other variable. So basically that's L over Y matrix multiplication with W transposed. Okay, and we know what W is. W is this thingy. So we know this one. This is this thingy. So it's going to be 2, 10, 10 matrix multiplication with 1, 1, 1, 1 because it's transposed, but it's the same matrix. And you just do this, and it's going to be 12, 12, 20, 20. No, 4, 4, 20, 20. Sorry, my bad. 4, 4. Okay. And then we do for W exactly the same thing. I said Y equals XW. We want W. We remove W, put D out, and transpose the other thing. X transpose multiple this. Okay, let's do that. Let's take x. X is this one, so it's 0, 1, 2, 3. That equals 0, 1, 2, 3. That's x transpose multiplied by 2, 2, 10. 10 if I'm not doing a mistake. Yes, okay. Let's just do it now. This was 0. This is 20. Again, the same thing. And this is 32. Right? And 32. Yeah. Okay, and that is the derivative of L over W. That's how we solve this exercise. I think the two last parts are the easiest parts because we have the technique to do these two thingy. Just need to show that you know how to do derivatives. But again, we remember that with these activation functions, it's element-wise. This one is quite easy to get because it's just taking the sum or this loss function accordingly. What is according to each one of them? It depends on, of course, the loss function that we give you. And then just to find the activation functions according to its input, which is almost always element-wise, unless it's softmax. But doing it with a softmax would be a very asshole move to give you, because that sucks. So that's it. Any questions about that?
No, thank you a lot. This helped.
I understand how these formulas with X make sense. I also wrote a comment piazza about them, but I don't understand the math proof behind it. If we open the chain rule, we have. Yes, okay. So, Nicolas, you're doing a great point. That's what you just wrote is a Jacobian. Yeah. If I just needed to do. Okay, let's just do. If I just needed to do y over x, that's a Jacobian. That's something that we do not know and do not want to be able to solve. We know how to open it up. It's just very, very cumbersome, and it doesn't help us in any way. The only idea that we can do what we did right now is because we always take this derivative, and this is this is always the same shape of the output. And more than that, as I said before, X is composed of some entries, and we care eventually how each of these entries is affected, not the matrix itself. Okay, we don't care about the matrix itself. It's just assembled in matrices and helps us to compute it in a computer. But what we actually care about is this thing. That's what I care about eventually. I don't care about the derivative of X as an input. I care about the entries of X as the input. Each one independently. That's what I solve. We saw that we can put them in matrices and actually do matrix some mathematical manipulations on them all together. But eventually, that's what I want to solve. I don't want to solve this. That's not what I'm looking for. I'm looking to do a scalar by scalar. But we just saw some mathematical tricks to do it in matrices. And the only reason that we can do that is because L is a scalar. That's all. So it's like shortcut to use. Oh yeah, definitely. That's the shortcut. It's it works mathematically, yeah, but it's simply a shortcut. It's simply a computational thing. It doesn't. It definitely not doesn't mean that dividing if X is an input to a function and you divide you want to find the derivative of the output of the function by X, it's W transpose. Definitely not. So as long as we're here, do you guys want to do do you want me to go over any other topic in the lecture notes? that we did, solve any exam questions together, anything. One more question on this. Okay, yeah. I don't fully understand why we compute DL/DF in this exercise. Would that make sense in a real neural network? DL/DF is the second, it's the first loss. It's the first derivative that we backpropagate from, Katarina. So it's just simply the beginning of the backpropagation. It's the loss derivative. But when we do,
it just looks trivial right now because we have a one matrix.
No, definitely not. Definitely. Oh, sorry, Benjamin. So basically, it really depends on the loss function. If the loss function is x to the power of 2, like MSE, that we like to say in this lecture, right? So definitely it won't be ones, because this is 1 over n sum I n hat I minus y to the div. This is the loss function, right? The derivative here is definitely not once. In this specific example, when I just summed over the entries, yes. And also it makes a lot of difference. Remember, yes, Jessica, I will do that. And remember when we talked about zero-centered functions, and how some of them behave differently. It's like, for example, if the loss function is in the CE or the BCE, like the cross entropy ones, that the derivative is always negative in the effective range, which makes a lot of difference for our optimization. A question before we go again to GAN, I will go over it. Is element-wise multiplication because F is element-wise function. Is element-wise multiplication because element, yes. Is matrix multiplication because, yes, exactly. That's Nicolas, thank you. That's a thumb rule that helps us to think about it. If the activation function, if the function that we're currently solving for was element-wise, the multiplication with the D out is always going to be element-wise. That's why, for example, when we solve it too, and do you want me to do also for sigmoid? I want you to do it yourself. Now, after everything we've seen, to do it with sigmoid, you can do it yourself. Sigmoid is just another function, like, and without this, not in corresponding to these numbers, just in general, yeah. To show that the derivative of sigmoid, how to do this from L to sigmoid. That's something you should be able to easily solve. Just apply sigmoid in the forward pass. Okay, so before that, only activation functions that are not element-wise, are on the output layer. I would make it even better phrased and distinguish between the model and the loss function. The softmax comes with the cross entropy loss function. We eventually apply it on the output of the network, yes, but the network's output usually doesn't have any activation function on it. And so, for example, in one of the exercises, right, you could put it in exercise 9 when you did facial key points, you could have put tan H on the output on the logits, so it will push them between -1 and 1, and then it helps you to already fit into the right area. But besides that, softmax comes always with the loss function and not with the model. Are there any activation functions inside the hidden layers that not that I know of? Not that I know of. But usually it's just element-wise, just to make it non-linear for each one of the different entries. Because softmax has makes sense to be not elementalized, right? Because we want to see the relationship between all our predictions to all other classes. But the derivative with respect to sigmoid is just applying the Stanford rule again. Yes, it's just doing the exact same thing. It will not be like X and W because sigmoid works differently, but it will be exactly like we did for F here. L over F is L over sigmoid. That's what you need to do. Just it won't be 1, 1, 1, 1, right? It will be something a bit different. You could also find a solution on Piazza. I've already posted it. Okay, let's do guns. Lecture notes, lecture notes. Here come the lecture notes. Okay. So guns. Okay, guns. Again, I will say that this is an explicit way, not in an implicit way to learn a distribution of some data. Okay, while VAE that we saw here is an explicit way to learn those distribution. We actually say these are mu. This is the log variance or the variance, or STD, and we learn with some loss function that learns distributions. With guns, we don't really do that. We don't have any loss function that implies any distribution. It will do it implicitly. What does it do? We have the data set, for example, the MNIST that we see here. And we have, we simply, at each iteration, we sample a batch of latent spaces from the normal distribution of 0 and 1. Okay, this Gaussian of 0 and 1, normal distribution. We sample that. We feed it with, we can shift it a little bit, shift and scale with some parameters, and we feed it into the generator. We feed it in the generator, it creates garbage completely. This is garbage, and the output is garbage. It's not 4 currently. It will be after training. Then we sample random images. It doesn't matter which image you sample. You sample random images from that number of the batch that we had in the same here. So each one of the vectors here, or the reconstructed bullshit, will have a corresponding real image. This is fake image, real image. Then we push them both together to discriminator independently. They don't care about each other. So basically, if the batch size was 4, now the batch size is 8. Okay, we both push them both. You don't have to do it if you don't have enough computation. You don't have to do it both in the same time. Actually, usually we don't. Okay, now what is important is when we do that, when we do this. So the training of GAN divides into 2. We first push these with label of 1. So the GAN needs to learn that the real images belong to class 1. Then we push these images, the fake generated ones, into the discriminator with class 0. Important, in PyTorch, there is a function called, if this is my tensor, so I can do x.detach. Detach means that I do not, so this is a copy of my tensor, the same entries, but it does not keep the computational graph for this tensor. Meaning, so basically I will do x fake or something, I don't know. So the gradients, so basically now I'll do discrimination. I will do classification. This one will be tries to send to 1, and this one I will try to send to 0, and only the discriminator will train for that. Okay, because I don't want the generator to learn from gradients that when I try to label its outputs to 0. So the first stage I do this discriminator with no gradients that flow on this branch. Okay, after I did that, after I updated the weights of the discriminator, I push them again, but now connected, okay? Now without detach. And I say, I want them to be label 1. Actually, I want you to discriminate them to 1, meaning now when the discriminator will say, will try to push them to 1 and push gradients also to here, this one will say, aha, I want to create something that the discriminator is able to discriminate as 1. And that's like the ping pong game. Each iteration, this one, the weights of this will change to try to, this will be 1 and this will be 0. And these weights will change while trying to make the discriminator do it with 1. Okay, and this is the way we learn the distribution of this data set. We still take, every time we take some generated random noise, but the generator learns to reconstruct real images, or at least approximate to real, as much as the discriminator is fooled to say if they are not real. Now, the loss function of GAN for the discriminator, it's basically the BCE, right? Basically the BCE, it will be a binary cross entropy loss, where 1 will be of this and 0 will be for the generator, for the output of the generator. So you could see, I think that's true. It will be, maybe it is 2 over n because we do actually 2 of the batch, right? So basically, it will be, oh, that is not true. That should be this thing. Okay, so basically it takes 1 for real images and 0 for fake images. And the loss function of the generator is basically try to maximize the value for the generator to send me to 1. So remember, that's very close to the cross entropy loss. That's basically the definition of the cross entropy loss. Also, I need to, I know a lot to fix. Wait, what did I do? Stop annotation. Okay. Any questions? Must be any question. There must be some questions.
Could you re-explain the label thing? So when the label is 1 and when the label is 0, and
yes,
how do we stop the gradients from flowing to the generator?
You don't really need to know that, how you stop the gradients to flow. There is just in PyTorch, if you see implementations of GANs, you'll see the function detach. Detach takes a tensor, X, for example, and says, let's copy this tensor, but without the computational graph in the background. So it will not have any connection to, doing backprop, it will not have the connection to the generator again. It will have, when pushing to the discriminator, yeah, or it will have gradients until here, until it's pushed here. Okay, so we have 2 stages of GAN. First stage, train disk. Okay, we push this one to with label 1, and these ones with label 0 to the discriminator. And we need to do classification, very simple classification, as we did in the very beginning of the class, with the BCE loss, okay? Then we do not take gradients in this part. We take, so for example, in PyTorch, we will have an optimizer, like for example, Adam. Okay, so gen optim equals Adam, and it will be a gen, let's say we called it gen dot parameters. Okay, so it takes only the parameters of the generator. So when I do optimization to this, it doesn't do anything here. So that was the first one. The second one, I take the same images, the same generated images that we use in the first stage, and push them again into the discriminator. But this time, I do not train the discriminator. The weights here do not change. All I wanted to, this time I tell the discriminator, oh, look at these images. Their label is 1. Classify them as 1. So it will say, it will try to classify them as 1, and will give us, of course, at the beginning, very big loss. And the generator will try to say, aha, I need to fool the discriminator and create something that is very similar to this in distribution. So in contrast to VAE, we don't have the construction loss, and we don't have the KL. We have simply classification of this is where the loss functions are. In the very, very, very simple version of GAN. Outside of GAN. But okay, let's see. But maybe it's not irrelevant for the exam. How can you say GAN implicitly? Because explicitly, it's like directly, VAE learns these distributions. GAN only does classification, and on the way, it learns the distribution of this data set. Implicitly, indirectional, not intendedly. The distribution is here. So we take a normal distribution, and the generator generates something from this distribution, something similar to this distribution. So the distribution is here. You don't have the mean and the mu, the mean and the STD. You simply generate something from that distribution. Okay, so the question, we also had question about an exam. At the end, we want the generator to be able to generate images that would be classified mostly as 1. But the discriminator, yes, that's what we want. Meaning now we have learned the distribution. Yes, that's what we want, exactly. Okay, let's move. So I'm going to stop sharing now from here. Stop share. And let's do exams. We said which one? 2021? Exam release, 21, and summer semester 21. Okay, Zoom, share. Okay. And we wanted which one? Where is the chat? Where is the chat? 1.6. Okay. Which of the following activation functions are not suitable as activation to add nonlinearity to the network? The way we do it is basically let's just put minus in each one of them. Okay, I'm sharing this screen now. Let's annotate. People killing, people dying. Wait. Okay, so we'll just put -1, 0, and 1 in each one of them, and let's see what happens. This we say it's not suitable because it suits really specific versions of neural networks. So we say usually it's not something to go to do when we do activations, and also because it repeats itself. How you say it in English? So that it's not discrete, or it's not one-to-one, you know. Anyway, like a few numbers could have the same value. So basically, what we will do is we'll just put it here. So not suitable, meaning they do not introduce any non-linearity. Let's see. If we put -1 here, that's going to be 0, and that's going to be 1 minus ReLU of 1 gives you, so 0 minus ReLU of 1, it's -1, right? 0, 0, 1, 1. So that's the identity function. Log of ReLU, ReLU of 1, of -1, that's log of 1, that's okay. Of 0, ReLU of 0, 0, that's 1, that's okay. ReLU of 1, that's 1, log of 2 is okay. Because it has the ReLU here. Okay, that's why it's non-linear. But it's so log here, if you do log 0 is undefined. So -1, for example, ReLU of 0, 0, it's undefined, and bam, not working. At the end, we want the generator to be able to generate images that would be classified. Oh, yeah, okay, we've already been there. So it's more about which one would work and which don't. That's the question. This one is, this gives the identity function. This one, log is not defined for log 0. If you put here a -1, and then it will be ReLU of 0. This, yeah. This one is the identity, yeah. This one is undefined. And since sin has nothing. Nicholas, because it's, I don't remember the wording in English for this, but it has this sinusoidal behavior. So this number of x and this x have the same value, and it's a very problematic thing. And it usually doesn't work well at all with regular neural networks. In some specific cases in physics, it does, but we do not take it as granted, as usable. Ambiguous, repetitive, ambiguous. Any more questions? A question from exam, from the lecture notes. Can you repeat what you said before about average pooling of filter? It's a disadvantage because the gradient is really small. 1/100, it cuts the gradients in 1/100. Remember that sigmoid, if it doesn't saturate, yeah, if it's just all the values of, for example, are at the 0 where the gradient is the biggest, which is 0.25, it's still very small. So if you backpropagate, you multiply again with 0.25, it diminishes. And if the network is really big, the gradients really vanish. With average pool, the gradients that each entry gets is 0.01 with this one. Yeah, the gradient of max pool will always is dependent on the size of the kernel. Like with 0, like 1/9 is not the worst. It's still worse than sigmoid, but again, the identity function. Let's put -1. -1 here, z. Okay, let's -1, 0, and 1. Let's put -1. This gives a 0. This gives a 1. 0 minus, right? ReLU of 1 is 1. 0 minus 1, -1. Do it with 0. 0, 0. 0 minus 0 is 0. 1. This is 1. This is 0. 1. Identity function. Jessica, do you want me to solve the winter semester 2021? Do you want me to open it? Uh, 1.5. Okay, exactly the same thing. Okay. Batch norm on ReLU and ReLU on batch norm. Okay, let's assume -1, 0, and 1. Let's assume that we put batch norm normalizes. Okay, so so remember, batch norm takes a set of values, right? If you set some of them to 0, the normalization will be different if you first take them without setting them to 0, right? These functions are not going to be the same. The input to them is not going to be the same. Okay, that's why this doesn't work. And also remember that this is not element-wise that helps, because dropout and ReLU are working on each weight or each activation differently. So dropout, let's say that these dropouts sets the same entries to 0, otherwise we don't have any to talk about. So let's say it does and does not activate things, drop something to 0. Let's say it doesn't drop X. Yeah, it doesn't drop X. So dropout always gives 1 or gives the exact same number. It gives X. Okay. So here it returns X into ReLU. Here ReLU X went into ReLU, dropout didn't change it. Okay, let's say it does drop it. So dropout gives 0, ReLU on 0, 0. ReLU gives something, dropout puts it to 0. The same thing. Max pool, ReLU. Max pool is so you could say that that's the same thing, like max pool returns X out of the kernel or does not return it out of the kernel. So it's exactly like the same with dropout. It's exactly the same case. Is it set to 0 or returns it? And sigmoid, of course, changes accordingly if it's 0 or not. So, for example, if X was -1, it would be now negative, positive, and ReLU will return it and it will not set it to 0. But if the neuron saturate dies, it might be different. Where in sigmoid, which one are you talking about? Everyone here was ReLU. Yeah. So here, if the saturated, it might be different. Max pool. So, but if X is the biggest one out of all of them, yeah, and so if it's negative, everything else is also negative, so it will all be zeros. If it's not negative, if it's positive, for example, it doesn't change anything. Does it answer your question? Like, for example, if x equals -1 and in its kernel, it's the biggest, so this is the one that's returned. Yes, so there is no max, but it will give me 0 in both of them, right? And if x is positive, it doesn't change. Sigmoid ReLU keeps the output. Yes. Yes, Q. If they are negative, yeah, okay, I think we've answered that. Any other question? Or what would you say the most important thing that we should keep from transfer learning and representation learning? What is representation learning? I don't know the term. So, 1 second, that wasn't the term for the second thing. Okay. Okay, learning the latent space, yeah, okay. PDF, like, there are a lot of things in the advanced lectures that I don't understand why we give you that, but that would make sense, learning a latent space from an encoder. So what is the most important thing? Transfer learning helps you learn from already converged, for a model that converged on a bigger data set. So it is not overfitted. So the starting point is really, really good. And it will basically allow you to not overfit to your small data set if that's what you're trying to do, like we did in exercise 8. And learning about autoencoders, you need to know everything about autoencoders, about what's the point of the encoder, what does the decoder do, why is autoencoder better than PCA? PCA is just a linear way to compress data, and autoencoders are non-linear to do compression of data. What is this meaning? What are the meanings of the latent space? Why do we want to work on latent spaces? Because you can learn many different manifolds. It's much easier computationally because the latent space is usually much smaller than the original image. It's much more flexible. You could learn, for example, distributions over the what else? What else do you want? What do you want from me? I haven't studied much. Okay, so before we go to another lesson, so let's do a question about autoencoders. Who can tell me? Okay, so we have, I think, a question from Nikolaus. We have to explain this again. So first of all, we'll do a question about autoencoders. Who can tell me what are the problems if the latent space is too small? Underfitting, very good. What will happen if the latent space is too big? Overfitting. Okay. Yes, and we basically do not perform what we needed to do with autoencoder, which is to compress stuff. Now we'll do this thingy. So again, if X is the one that is picked by max pool, this doesn't change. If X is not the one that if X is not picked by max pool, it will be 0 no matter what. Both of them will give 0. In X is the one that's picked by max pool, it means that it's the biggest in the kernel, and it means that either if it's negative, it's picked by max pool, this is sent to 0. If it's negative, this is sending to 0 no matter what. If it's positive, it will pick by max pool, and ReLU will keep X. The result will be X. The result of X is of ReLU on X, if it's positive, is X, and of course this is the one that's picked, so it keeps X. That's this thingy. Can you give a brief summary on how to go from latent space to reconstructed images? I am not sure what you mean by that, because it's simply just doing a decoder on a latent space and getting an image, and then using a loss function to guide it. I'm not sure.
Yeah, so I meant so there are several ways on how to like increase the size. So you go to latent space and you have to like get again the size of the input image. So you can upsample, you can do like transpose convolutions, and you can do like up convolutions. And I'm a bit confused on what's the difference between all of them.
Okay, so the thing is that you should be much more specific, because we were talking about autoencoders, and autoencoders, we refer to them as fully connected layers, fully connected models. So when we talk about upsampling, thing is, it has to be in convolutional autoencoders or units, okay? Just for the sake of consistency.
Yeah, I mean, fully convolutional autoencoders.
Yes, okay, so just a sec. Let's stop share it here. Let's share it here. I'm sharing now, sharing away. Come on, work. Doing convolutions, transfer learning, that's optimization. Okay, so we have two different ideas that we've learned in the class. One is upsample, is basically taking this one and upsampling to a bigger one by using some kind of interpolation. Either it is the nearest neighbor, be linear interpolation, or be cubic. It's just linear, not learnable algorithms. Then therefore you should always add some convolution to it to add some learnable features to it. The other way to do it is transpose convolutions that work completely different. And I will not explain how it works, but what you need to know is how that it adds, it's a learnable function. So instead of doing first a linear thingy and then convolutions on it, you could immediately do it with parameters. If you want to know how to do it, there is a very, very good video and some summary that for some reason is not here. I thought I did put it here. So basically, so you could watch it. It's quite cumbersome to understand what's going on there. But after 2 hours, I guess you could wrap your head around it. You don't need to know it. You just need to know that it exists.
Yeah,
you need to know that this is linear and this is non-linear. This is not learnable and this is learnable.
Yeah, and my question was, so what does up convolution have to do with all of this? Because
what is up convolution? I don't know what up convolution is.
Okay, then we just have to know these two methods, because at some point I read up convolution. I don't know if in the lecture notes or in the slides, but I was a bit confused.
I don't know. Yeah, I either don't know what up convolution is.
Okay, perfect. Thank you.
You're welcome. I don't quite understand the second one. Does encoder have latent space, lower dimension also? Does I don't understand your question, Q. I don't quite understand the second one.
Yeah, this is the solution for the question about the advantages of UNet over autoencoder.
Okay, I didn't ask that question, but okay.
Yeah, so but that's in the lecture notes.
Okay, so what do you want to know? Doesn't auto?
Yeah,
both of them
about
have
the second.
lower.
Right.
I don't. Which one can you point me out, because I'm not sure what we're talking about. Did you?
I think. Let me open.
Like the three advantages over skip connected unit over. That's what you sent, right?
Yeah.
Allows making most of the calculation process in low dimensions for a fraction of the cost. For different input sizes, minus. Okay, and you asking about doesn't it have space?
I'm asking if that's really an advantage, because autoencoder does have the same thing.
Yes, okay, but here we're using convolutions and not fully connected layers. You could represent.
So I think you should rephrase that if you use convolution, then you will have a lower computational cost.
Yeah. I have a lot to rephrase actually, and I did not keep any. I did not keep the notes about it. It would be nice to if you post it on Piazza or something that I could relate to it.
Okay.
Thanks. Okay, there was a question about what's happening on my jaw? Skip connections. I haven't studied it much, but exactly what you mean, highway or gradient, we're talking about skip connections. I get the idea that we can just jump to the start of the skip connection using XL, but we still have to update the weights inside the residual block, so we don't get to simply skip backprop. No, the function of the res block itself doesn't have skip connections. It has some gradient. But it does have a fully connect, because it's the input, it's part of the input to the next layer, then it gets fully magnitude of the gradient. So it also gets very good, well maintained gradients. It has learnable parameters and it has backprop, and it gets just it's like a sub network within the network, if it makes any sense. Do we need to memorize or know the derivation of BN optimization techniques? Yes. Okay, both of them are the input to the next layer. This one gets gradient, this one gets gradient. This one gets it from both ways. This one gets it only from here. But both of them have gradients. I don't see where the problem is. Maybe you could elaborate. Yes, exactly. That's what the questions of showing the highway of gradients. This is the f of x, and this is for x. That's why we have the one here. It will have, I wouldn't say more accurate, I would say it will have a much bigger magnitude. Okay, so unless we we could be done less than, I guess, 15 more minutes. After all, that's I think we're done. Or do you guys have any more things? Multi-head attention, but if, for example, there is a question that says calculate the importance of token high, you should know what are the embeddings, what is what does self-attention mean? What do we want to do there? Why do we use decay or softmax? Like, how do we get the embeddings for the inputs? Like, how are they generated? What is positional encoding? But you don't need to calculate their stuff. That doesn't make it, like, that's something a computer does, not you.
I mean, if we still have time, why don't we, if no one else has anything, try to do the typical task of representing a fully collected layer with convolutions? I think that's good practice, right?
I'm not sure in what way it's a good practice of what exactly. Is there like a physical, like a calculation?
Oh, I don't know,
step?
like 1x1 convolutions, and then showing sort of like, you know, how we have to spec out the convolutional layer.
So
It's just
basically,
an
if we
idea.
have
I don't know.
if we have a B, C, H, and W, and I want to use one-on-one convolutions, and to do it as fully connected layer, I could do it in a single, just modify it in a single way, B, H, W, C, which is in PyTorch, it's or permute. This is a transpose or permute, it's the same thing. Permute. 0 stayed in place 0. 2 and 3 come here, and this one comes here. 1, this is 0. 1, 2, 3. 2 comes here, 3 comes here, 1 comes here, meaning C is here, and then I can do fully connected layers, which is like exactly like one-on-one convolutions. Because flattening it, so remember that in a convolution, we want to do this, not all of them all together. Wasn't the question. If you want to take all of it together to do a fully connected layer of the entire images, but if you want to represent no, like that's not of the questions. You can try to represent fully connected layer on that with convolution, taking the entire kernel across the channels as a special size. But if you want to do just one-on-one convolutions, you have to do it like this. You have to transform it like this. So basically, that will transpose to 3. Wait. What does one-on-one convolution mean? Unless, of course, it can if you flatten it first. One-on-one means this is the kernel size. If you flatten this to one single vector and apply one-on-one convolution, that's exactly like doing fully connected on an entire image. Of course, as long as the one is, or you have, basically you have B, H multiply by W by C 1 1, and then you have a 1 1 1 convolution. Yes, but I don't want to do the entire image. The question was, how do I perform 1 on 1 convolutions with fully connected layers? That wasn't the same question. I don't want to do the entire image.
Well, no, I think Chad was right. I was referring to the classical example of saying, okay, let's rip out the fully convolutional layers at the end of a network and replace them with, let's rip out the fully connected and replace them with convolutional layers. So I think they meant the right thing, no?
Okay, if that's what the question was about, definitely, yes. If you want to take the entire input of the image, you have to either flatten it, depends if you want to, and instead of flatten it, you want to do with fully connected layers, with convolutions, you will have to take a kernel size of the entire input of the same. So you have to take, if this is H on W, the kernel H will be H. Any other question? Something from exams, something from the lecture notes, something. Yes, of course. Yeah, definitely. In most cases, they are different, actually. Okay, any modern data set from autonomous driving has different H and Ws. Not for the kernels. But what is the benefit of using exception layers? You could just have, you don't have to pick between different things. You can have everything. But there is a huge drawback of using exception layers, which is computational. It doesn't really improve the net anything, and computational effort. Something that you might think that can be distracting to students' future, i2dl course. You try different filters to capture things of different sizes. Okay, interesting question. Because otherwise I could just pick stuff from here, but I think we've done everything already. But I think it should not come, it should come as it's not as important for the exam. If I ask you to do the definition of weight decay in the optimization, like you're using SGD with weight decay. Given alpha, which is the learning rate, and lambda, sorry, which is the coefficient of the weight decay, can you do the optimization step for WT plus 1? Okay, for your keyboard, let's just do A and G. A is learning rate, G is this thingy. Remember the optimization step, the optimizer step, not the loss function. Okay, very nice. At the popular architectures, you need to know the basic why they did things. Why do we use convolutions here? Why do we use fully connected layers? Can they take different input sizes just out of the box? What is the bottleneck? I mean, what gives, so AlexNet has 60 million parameters. Where does it come from, these 60 million parameters? What does the influence of such big kernels? Katerina, let's see, very good. Very good. What is the influence of such big kernels? For example, who can tell me what is the problem with doing 11 on 11 convolution? I want 2 different disadvantages. Okay, very good. Seems to me like someone is ready for the exam. Then every filter after that will use a separate field. There's no problem with that. Losing locality, yes. So we can't extract eyes, for example, computationally expensive. Very good, very, very good, very good. Okay, where does this come from? 60 million parameters, who can tell me? Fully connected layers, very nice. Okay, let's say we wanted to reduce this this huge size of fully connected layers. What could we do in order to reduce this size? Another pooling. Instead of, it's reduce this. So I would do it instead, reduce the spatial size. Yes, apply full. No, fully convolutional layers will be the same because we want to, the entire point here. Why do we have fully connected layers here? Classification. What do we need to classification? Global features. Very good. We need global features for classification. Therefore, we have to have them. If we wanted to do it with convolutions, it would be the same thing because we just demand a matter of structure of the weight matrix. But we do need the global features. We could just add more layers, of course, if we wanted to. But if we add more layers, what is the problem that arises? Vanishing. It's very good. Okay, another question was, why can't we simply change feed it to a different spatial size, another resolution, it's the same thing, like 240 over 240. Why can't I just do that? Why can't I? Why isn't it possible? So let rephrase it, Christoph. Rephrase it.
They take a different, like they take a defined number of parameters.
Not defined, a fixed one.
A set, yeah, a fixed one. Yeah.
Good. So basically, both of Jessica and Q, you are correct to some extent. But that's also not true for fully convolutional networks, because we can't just take because they're not scale invariants. Here, because of this will just give us a bug. If it was just fully convolutional network with no fixed parameters, like the kernel size will be 3 on 3 on all of them or something, it will not raise a bug, but it will be a problem if you don't continue training. Here, that will just simply not work if you just change the input, because it expects a very specific number of neurons in the input.
So I raised the question about the popular architectures because, like, the questions you ask now, they're not specific towards the architecture, but they're just more like, in my opinion, they're more like, in quotes, common knowledge about deep learning.
Mm-hmm. So that's what they come to represent. That's what they come to represent. Like AlexNet, We could ask you, in AlexNet, we did this. Why did we introduce, what's the problem with introducing 11 on 11? Okay. LNet was the first one and used TANH and sigmoid. What is the problem with that?
Okay, so basically we do not need to know how those popular networks are structured. So you would give us, for example, the figure and just ask a question like
one example question.
11.
What example? One example question was this one time. Like give the global idea of Elinet, and then it was something like this. Not it wasn't an open question. It was a multiple choice, just to show that you have conv, pool, conf, like the main idea. And then catch what you do to reduce fully connected layers in the end, and catch what we can do to reduce. We can go deeper and then do more, reduce the special size even more to 2 on 2 or 3 on 3, and reduce the number of channels. So this flattening and doing from fully connected layer wouldn't be that big.
Could we do one by one convolution also?
Yes, you could do one convolution to reduce the number of channels, for example.
So basically for this type of question, this image would be given, this figure of AlexNet.
And depends what the question is.
Okay.
Like to ask you how many parameters in AlexNet, I don't think it's relevant. You know?
I'm just trying to figure out what to remember from these popular architectures and what not.
Like you don't need to know them by heart. Definitely not. I would do know that VGGNet, what it did better than AlexNet, for example. It did this, the 3 on 3 convolutions. And why is it better? Like, why does residual blocks allow us to go deeper? I think they're going to ask about the idea behind. And in this case, we have to apply. Yes, batch normalization will really help us with going deeper. If it's fully convolutional network, can we put different image resolutions? I guess we can. It won't catch an error, but output won't be good. Yes, exactly, Nicolas. Exactly. Because this is the answer that Jessica and Q gave. Convolutions are invariant of scale. Now, if the input is bigger in context of what, for example, Adobe does, that you give it an image, yes, and then it builds something in the background of it. Yes, so the objects there are the same scale, then there isn't a problem because the image of the same scale. But if you just take this image and you upscale it to something bigger, then it doesn't know to work with it well. It's invariant to this upscaling. What else? I think that's enough for today.
Okay, maybe sort of as a conclusion, as you said, sort of the very last exams were quite repetitive, and so you're trying to mix it up a bit. Is there anything that we should watch out for that doesn't really come up in the last couple of exams that we should be aware of?
I don't think they were repetitive. If you look at the last exam, that was completely creative.
Okay.
So I think this one is going to be bored down to earth. Anyway.
Oh, okay.
Because we saw that people are not. For example, in the last exam, let's just. Oh fuck! I'm sharing my. Stop share. And let's go to examination.
Dan, what would you say is the best exam to prepare? Like Oh,
I don't know.
which
I
exams?
honestly don't. I don't know. I can tell you which not to take, and that's the 23 winter semester, like basically last semester. That was a
Okay.
horrible exam, but filled with mistakes also, unfortunately.
Okay, so I'm not gonna touch this one. Thank you.
So I wouldn't practice with it. I would solve the questions, of course, but I wouldn't practice with it like as a simulation. So basically, this question last semester scared a lot of you. A lot of you actually, many actually managed to solve it. And what made it a horrible exam, that people really didn't practice. So all they did is to read the lectures and the slides, and of course from the slide they didn't know anything. So for example, this question is like intimidating from the first look, but all it's asking is the difference between fully connected layers and convolutions. That's all it asks for, and people just didn't know what to do. Like they lost their shit. So basically what happened here, we gave you a point cloud and we explained what a point cloud is. And then we ask you, why is it if I want to extract something from that point cloud, yeah, that each point is independent of the other, why should I use on this fully connected layers in some manner and not convolutions? And the idea was, if you flatten this out, if you flatten this like an image, and then you do fully connected layers, you have global information about all of the points all together. When you do convolutions, the convolutions also assume structure, which they don't. That's something that, for example, one of the questions. And then it was about reshaping data, like things that we just did together, right? For example, with the one-on-one convolution. How do I reshape the tensor? If the tensor is R, wait, you can't, like, if the tensor is RCD, for example, or in a B and D. B is the number of batch, N is the number of points, and D is the dimension. Yeah. How do I reshape it to use fully connected layers? I flatten N and D. That's something you did in exercise 3 and 4. So that's something that we expect you to know because you did that. And a lot of people just came unprepared. So like every semester, we have the same thing. There are 1,100 students, about 1,000 taking the exam. And how many of you were here today? About 20, right? So a few actually learned the material and a few actually knew how to solve stuff. A lot of them just saw the lectures and thought that would be enough to solve the i2dl exam, and then raise a cry about it. With some things were completely right. Some of the things weren't formalized well. And we had to we accepted it, and we gave points. Of course, we don't want you to fail in any way. We're here, we're doing everything we can, as you could see, so to prepare you well to the exam. But that's just the cry was about that people saw these kind of questions and lost their shit. But for example, this question was, I don't know why they put it here. Like I needed like half an hour to solve it for the first time. So it doesn't make any sense. So that, of course, makes sense. Why do you put it here? So, of course, it was a hard exam, definitely. I'm not saying it was. It was really hard exam.
Maybe one last question. It's well, it's regarding the organization of the exam. So there are different rooms for the same exam, right? When do we know which room, in which room I write the exam?
Yeah, you'll be assigned something like a week before.
Okay, so we get an email basically.
Yeah, not an email, but you'll see it in Piazza.
Okay. Could you maybe like send the Piazza note out as an email as well? Like, let us. Like, I think there's an option to let
Yeah.
us be notified
Thanks.
via email as well.
Mm-hmm.
Okay.
Yeah.
Perfect.
I like it's not up to me. I'm not the one who do that, but so I guess it would be this. But we could try and send you an email when it happens. How long would you recommend to allocate it? How long would I allocate here? If you're stuck on something more than a minute, move on. That's what I would do. Just move on. You for the strategy, move on. You don't know something, don't try. You know, like don't even break your head on it. Come back to it later. There are enough places to get points. First of all, if you're stuck on something at the beginning, it will destroy your mood for the entire the exam. That's why I want you to do simulations. If you don't know something, continue on and let yourself solve things that you do, and it will let you feel that you actually managed to solve something, that you've gained points, enough points, so you comfortably come back to other things, so you're not in a rush. That you could solve them, or not solve them, but you'll know that you've already accomplished something, so you're not completely failing or something. Will the exam rooms be ventilated? That's TUM, they're not. So, I don't know.
Unless you get into Niesner's office.
Yes, if you sit on Niesner's lap, then definitely.
Are we allowed to take some kind of thing to refresh? Like a fan?
I think there won't be a problem if you do, but if it doesn't disturbs your fellow students, maybe, like, of course, you can bring some food and water. And I don't know. It's going to be 8 o'clock in the morning anyway. It's not going to be that hot.
True.
Don't worry. Do we have questions about other data types like point clouds? No, what we know is images and embeddings for convolutions. That's what we know, right? Or RNNs, for example. I think that's all we know. Okay, guys. So I think that's enough for today. I'll go celebrate my birthday properly. I'll see you next time.
Happy birthday! Why didn't you say so sooner?
It doesn't matter.
It does. Happy birthday.
For me it does, but yeah, I'm an old man. Okay, so I'll see you next time.
Thanks for your time. We really appreciate it.
Of course. Bye-bye.